shortlisted the candidates for the flash talks.
Oh,
so they will
okay.
try to put it on a slide, and we will just show it up first, and then switch to your slide.
Sounds good.
So that's what we are doing.
Okay.
Just give me a minute. Sure.
Yeah. Apparently, there's one more thing that has to be done before. Hey, wait, here we go.
All right, I'm so sorry, everybody. There was a few arrangements that we had to do in the last minute. So before we start with our next presentation, I will announce the shortlisted presentations for the next session for our UNAM Flash presentations. So again, after a rigorous evaluation process, we shortlisted the presentations, and it will be showing up very soon. So those are the people that will be presenting at 3 p.m. Following the order, so the first presentation will be Azimati, Aykeber, Ali Kalantarifard, Elif Duman Ergül, Eliza Sabub ve Kova, Hamit Resuli, İlkay Çisil Köksaldı, Melis Özkan, Muammer Kanlı, Murat Serhatlıoğlu, Nimat Hagipur, Onur Erdem, Rojin Gaffari, Sezin Galioğlu, and the last presentation will be Talha Han. Just to let you know, this will be a very strict 3-minute presentation. If these people do not show up, they will lose their chance, so we will just move on with the next presenter. Okay. Ali, can you ask him to switch? Okay, so now we will be moving on with our next keynote speech. Chris Toumey is with us today. Professor Toumey earned his PhD at University of North Carolina, Chapel Hill. Currently, he is at University of South Carolina, and he works in the anthropology of science, and for the past 16 years, he has been working on societal and cultural issues in nanotechnology. Chris is the author of more than 90 publications on nanotech, including his commentaries, which appear 4 times a year in the journal Nature Nanotechnology. 2 months ago, his book, Nanotech and the Humanities, was published by Cambridge Scholars Publishing, and let's give him a warm welcome.
Thank you. Thank you. Well, thank you so much for including me in UNAM's NanoDay. I appreciate it. It's an honor and a pleasure for me to be here. I like that very much. I also appreciate being on the same program with Monica and Tomas. My presentation will be very different from theirs, but if it is approximately the same quality, nevertheless, then that would make me very, very happy. So I'd like to introduce myself and my work, if I could. You've heard that I work in the anthropology of science, and I've learned that hardly anybody has ever heard of anthropology of science and wonder what it is. But of course, you've heard of history of science and philosophy of science and related disciplines. So that anthropology of science is the newest member of that family, if we can put it that way. And I want to tell you a little bit about the kind of work I do. I'm an academic, and so I write peer-reviewed articles, and most of what I write about these days is nanotechnology. So I've done a series of them, maybe about 3 dozen, maybe 40 articles like that. And then there's something else, and this is probably the way that I'm best known, which is that 4 times a year I have a short commentary in the journal Nature Nanotechnology. And this is my platform for showing the readers, particularly the scientists and the engineers who read Nature Nanotechnology, that the humanities and social sciences can contribute to our understandings of science and technology. And so I've had something like 55 or 56 of them so far at this point. And then the most recent thing that's happened in my career is that 2 months ago, my book on nanotechnology was published. And if you want to see how to order a copy, I can show you that with this here. And then I want to tell you about 2 more of my activities, which is that once a year in the spring, I take a group of chemistry students from a local high school on a tour of several labs that are related to nanotechnology at the University of South Carolina. And we talk to them a little bit about what nanotechnology is. These are very bright young people. That's not very difficult to tell them. And we explain briefly the operating principles of the atomic force microscope, the scanning tunneling microscope, the transmission electron microscope, and the scanning electron microscope. And then we take them to several labs so that they can see that. So in this situation here, the fellow on the right is a postdoc in a lab in the chemistry department at University of South Carolina. And he's explaining to the high school students how the scanning tunneling microscope works. They don't get to see the STM operating in real time because it takes about 24 hours to prepare the instrument, to get it to very high vacuum and very low temperature. But they get to understand the general principles of that. And then here we have one of our high school students. This is Lucy, is her name. And she's sitting at the monitor of the atomic force microscope. And what we do each time when we go to the lab with the AFM is we have one of the students volunteer a strand of their hair, and then that's used as the sample, which is imaged by the AFM. And here Lucy is enjoying watching the image of a strand of her hair on the monitor coming out line by line by line until the monitor is full. And then there's something else that I had done in the past. I used to run a public engagement program called the South Carolina Citizen School of Nanotechnology. And when we did that, we would meet 1 night a week for 8 weeks. And the important thing about it was that it was a dialogue format. It wasn't just the experts talking to the participants, but a really good dialogue back and forth between the experts and the participants, most of whom are from the lay public. And so some of the events were lecture type formats with a whole lot of dialogue. That's the top picture there. And others were lab tours so that they could see some of those instruments that make nanotechnology possible. Now, I've been asked to talk about a certain question. What will nanotechnology do for humanity in the future? And I have a preliminary answer, which might disappoint some people, especially UNAM. And the answer is, I don't know. and I have 4 reasons for saying that. So what I would like to do is I like to use those 4 reasons to explore nanotechnology, to understand and appreciate nanotechnology, so that later on we can circle back to the primary question and say some things about the future. Well, the first reason is, as you know, nanotechnology is not a single technology like a better smartphone, and it's not a single process like maybe polymerase chain reaction. Instead, it's a very large group of scientific and engineering disciplines and subdisciplines and some technologies. So, for example, several kinds of physics, several kinds of chemistry, molecular biology, microelectronics, material science, scanning probe microscopy, electron beam microscopy, et cetera, et cetera. And in fact, considering that we have quite a spectrum of scientific disciplines and subdisciplines, I can imagine this. In the world of nanotechnology, the person in organic chemistry may have a lot more in common with the person in molecular biology than with their colleague down the hall in inorganic chemistry. So anyway, I mention all this because to answer that question, we have to be aware that nanotech means different things to different people, even within the same scientific discipline. So that's my first reason. Secondly, there are some applications from nanotech that are available now, and I'll talk about one of them towards the end of my talk. But most of those applications are in the future. Some of those applications are in the near future. Some of them are in the far future. Some of them we don't know yet how realistic they are or how fantastic they are. And so what this means also is that because most of the applications are in the future, that means that anybody can project their own vision onto nanotechnology, which means then for the second time that different people can project different expectations onto nanotechnology. So for example, some people want to know, will we have a cure for cancer, say in the next 5 years? Other people want to know, will we have molecular assemblers, and will we have self-assembling nanobots reproducing out of control in 40 or 50 years? And those are 2 very, very different conversations. Then I have a third reason, which is that nanotech is not a single technology. Instead, it's what they call a generalized multi-purpose technology platform, like the assembly line. So the assembly line was invented about 125 years ago, something like that. And the original assembly line was invented to assemble automobiles. And it was obvious that that was a good idea. If a very complicated device like an automobile has to be assembled, then the assembly line is the best way to do it. What was realized not long after that was that the assembly line is also a good way to assemble, say, washing machines and sewing machines, to assemble anything that requires numerous parts to be added in a long and precise sequence. Given that nanotechnology is going to do all sorts of different things, then we have, once again, the lesson that nanotech means different things to different people. Now, so far, these are 3 technical reasons why it's difficult to say exactly what nanotechnology is, let alone what nanotechnology is going to do in the future. But I'm going to add a 4th reason. This isn't technical, but this is still relevant, which is what we mean by nanotechnology depends to some extent on how we tell the story of the origin and the history of nanotechnology. So this is not a technical reason, it's an historical or cultural reason. So let's remember some of the ways to tell the story of the origin and development of nanotech. According to one story, nanotechnology begins with Richard Feynman's 1959 talk. There's plenty of room at the bottom. And I have found in my work that this is the primary origin myth for nanotechnology. And it has some implications. If we accept that this particular event in 1959 is the origin of nanotechnology, then there are some implications that come with that. Feynman's talk was based very, very much on quantum physics, which means that we would tend to see nanotechnology as something that is centered on quantum physics. However, there's a problem with swallowing this particular story. And the problem is, there's something I've seen and something I've written about, which is that Feynman's talk was largely invisible between 1959 and 1979. There was something really impressive about Feynman's talk, which is that it was published 6 times in 3 years in several different forms and lengths and variations. But I think that's really quite remarkable that, that something like this is published 6 times in 3 years. I'm very impressed by that. I doubt that any of my writing is ever going to have that kind of success. But I also found that in that 20 years between 1959 and 1979, Feynman's paper was cited only 7 times, published 6 times early on, but over a 20-year span, published only 7 times. Now, I have a colleague, Cyrus Modi, who's at University of Maastricht in the Netherlands, and he's found a few more of these for me. I think they were all in microelectronics. So we go from 7 to 12, but we're still saying only 12 in a period of 20 years. And most of the citations to Feynman's talk were in microelectronics. Okay? So anyway, my conclusion, which has not made everybody happy, is that Feynman's talk, it's brilliant and it's entertaining and it's readable, but it's not the origin of nanotechnology. So let us try a second origin story, which is that to some people, nanotech begins with Eric Drexler's 1986 book, Engines of Creation. And the problem here is that Drexler's vision of nanotechnology is based on what I would consider to be some far future fantasies like nanobots and gray goo out of control, molecular assemblers, and so on and so forth. And there's a problem here with this. On the one hand, Drexler's work is very, very popular with a certain large audience. There's no doubt about that. And he is certainly the main popularizer of nanotechnology. But what I have found is that there are very few scientists working in nanotech who embrace this vision. They do different things and they have different reasons, and they're not in any sense tethered to Drexler's understanding of nanotechnology. In fact, I find also that there's a fair number of working scientists who have never even heard of Drexler and his vision. Then there's a third account. This is the one that I'm closest to, but it could be wrong also. Some people would say that nanotech begins with the 1981 invention of the scanning tunneling microscope and the 1986 invention of the atomic force microscope. And let us note here that if we're going to embrace this vision, this means that nanotech began at IBM because Binnig and Rohrer invented the STM at IBM Zurich in 1981, and then Binnig invented the AFM when he was on a leave of absence. But there's another implication that goes with this particular vision, which is the idea that nanotech is driven by the invention of certain instruments rather than by visionary statements. And then there's another story which also comes out of IBM, which is that nanotech takes off with the Eigler-Schweitzer experiment. And you may or may not be familiar with this, but in 1989, thank you, yeah. In November of 1989, Donald Eigler and Erhard Schweitzer were working at IBM Almaden in San Jose, California. And they used the chamber of their STM to, first of all, get their high vacuum and their extremely low temperature, 4 degrees Kelvin. And they had a nickel surface, and they sputtered xenon atoms onto the nickel surface. And then over a period of 22 hours, they used the tip of the scanning tunneling microscope to pick up 35 atoms one by one and to spell something out. So that was published in Nature in April of 1990. So the process goes like this. They're showing you there in that central image that the tip is coming down very, very close to a xenon atom, such that the atom bonds to the tip, and then the tip is moved horizontally, thereby dragging the atom into a particular place. And this is done 35 times. And then in those 6 panels, beginning with the top panel here, this is when the xenon atoms are first sputtered onto the surface. And the point is, at this point, there's no structure, there's no order to them. And then an order gradually comes along here. And then they have made the letter I here. And then they have added the letter B. And they finish up with this image here, which is this. In other words, they've spelled IBM with 35 xenon atoms, just in case anybody had any doubt of who they worked for. And anyway, the important thing about this is that the STM was invented by Binnig and Rohrer at IBM for the purpose of creating accurate images of atomic surfaces down to and including individual atoms. The instrument was very much appreciated that way. And then the atomic force microscope was kind of like the stepson of the STM. But what Igor and Schweitzer did, and their work was built on other people's work from a couple of years before that, but what Igor and Schweitzer did was they showed us that the STM could be used not only for making images of atomic surfaces, but in fact altering an atomic surface atom by atom. And some people would say that that's really what nanotech is. I think actually, personally, that nanotech is a lot more than that. But if this is the most dramatic event in the history of nanotech, then some people like to think that the real nanotech begins with the Igor-Schweitzer experiment. Anyway, what all these different histories mean, and we could add 2 or 3 more if we had to. This reinforces the idea that we saw with Binnig and Rohrer and the STM, that IBM is the engine that drives nanotechnology. And I have a great deal of respect for the IBM contributions to nanotechnology, but I would certainly not say that, nanotechnology is kind of like the property of IBM. But anyway, this gives us another lesson, similar to the lesson that we saw from those first reasons, which is that given that there are multiple ways to tell the story of the origin and development, then nanotech means different things to different people, which makes it difficult for me or anybody else to say with a great deal of precision what we know that nanotechnology is going to do for humanity in the future. But that's okay. We're going to use these insights to get on to something else. We'll build on our knowledge of nanotech. And so I want to give you my 4-part definition of nanotech. And this is not my individual genius or anything like that. But what I'm going to say in my 4-part definition is a clarification of what I've learned from a lot of other people, including scientists. So I want to say part 1. Nanotech includes many scientific and engineering disciplines, as I was saying in the case of my first reason, plus several technologies, which serve primarily nanotechnology. So for example, I don't imagine that the scanning tunneling microscope or the atomic force microscope serves anything except studying matter that's measured by the nanoscale. Okay, so that goes back to the first reason. And my second reason is that these are scientific and engineering disciplines and subdisciplines for controlling matter. not merely understanding matter at the nanoscale, not only imaging matter at the nanoscale, but using that knowledge to change and improve things. For example, there's good reason to be optimistic that some forms of nanotechnology will improve medical therapeutics and medical diagnostics, we might add, and microelectronics and environmental remediation and material science and so on and so forth. In other words, nanotechnology is not merely a science, it's a technology. One way that I think of this is that not long ago, about a year and a half, 2 years ago, the space satellite, or space instrument, Cassini, visited several planets in our solar system. And its last visit was to Saturn. And it did some things that were remarkable that had never been done. Cassini moved into the space in between Saturn and its rings. Cassini came very, very close to the rings of Saturn to gain a great deal more knowledge about what the rings of Saturn are made of, and so on and so forth. And I think those are remarkable developments. And I find that very, very exciting. But I don't think that the knowledge gained in the Cassini mission is going to change my life or improve my life or make my life worse, or your life either, for that matter. I think it's great science. But if there's a difference between science and technology, it is that technology is intended to change our material culture. And so that's part two of my definition. We control matter for the purpose of changing and improving our material culture. And part three is that we're talking about matter which is measured by the nanometer. That is, as you know, a billionth of a meter. So we're talking about atoms, molecules, atomic surfaces, man-made nanoparticles, small viruses, et cetera, et cetera. And then the last part of my definition is that nanotechnology does these things largely by taking advantage of properties and forces and relationships that are unique at the nanoscale. So for example, catalysis is different, it's better at the nanoscale. Semiconductivity, molecular recognition, and so on and so forth. Those are some of the properties that nanotechnology takes advantage of. So, then this is going to be a mouthful. Nanotechnology is a large group of scientific and engineering disciplines and subdisciplines and technologies for controlling matter, which is measured by the nanometer, largely by taking advantage of properties, forces, and relations that are unique to the nanoscale. It's taken me many years, actually, to hammer together in my head this four-part definition, but I emphasize again, this is not my own genius, but this is this four-part definition I have learned by putting together the insights and the wisdom of a lot of other people. Okay, so what we've done here is we've seen four reasons why nanotech means different things to different people. And I hope that my composite definition will help us to narrow things down a little bit so that we can separate, the far future fantasies from things that are occurring right now and that will be happening in the near future. So then that enables me and you to return to that question, what will nanotech do for humanity in the future? And I cannot say everything that'll happen. I imagine there'll be thousands of things that'll happen, I think. But I wanted to concentrate, I want to finish up by concentrating on three of the most important applications. Excuse me just a minute. Come on, dear. Okay. So the first application, which I think is going to come into our lives before very long, I think within 5 years, 10 at the most, is targeted theories for cancer. I think you are familiar with the problem of chemotherapy. So somebody has a cancer. Chemo is a poison. There are different chemos that are put together for different kinds of cancer and different locations of cancer. And the way this poison is supposed to work is it's injected into the body through the bloodstream, and it's meant to be strong enough to kill the cancer, but not strong enough to kill the patient, right? And sometimes that works, and sometimes it doesn't work. Sometimes it doesn't work because for the sake of the patient, the chemo has to be limited to a certain strength so that it does not kill the cancer. And then other times we have the opposite problem, which is that sometimes the chemo has to be so strong to kill the tumor that it either kills or terribly debilitates the patient. So that means then that the holy grail of oncology, as I would put it, is to find therapies which go only to the cancer tumors and not to the healthy cells, targeted therapies for cancer. And there are, I think, 2 dozen, 3 dozen, 4 dozen different approaches coming out of nanotechnology right now. Some of them are clinical trials right now. I don't think any clinical trials in this have been completed now. And so nanotechnology has not yet delivered targeted therapies for cancer. But there's a lot of that going on, and I think a lot of it is downright brilliant. And so this is the first of the 3 that I predict is going to be in our lives in the near future. Targeted therapies that go only to the cancer tumors and leave the rest of the body alone. And we can talk about 1 or 2 of them in detail later on if we need to. So multiple applications are being developed. Some will be successful, some will not. They will kill some kinds of cancer, but I don't think there's any guarantee that all kinds of cancer can be eliminated with these medical therapeutics that are coming down the road. But you and I should not be surprised if some of them work and work quite well. And then that means that the medical treatment of cancer is going to be very, very different and much more successful than what we see today with chemotherapy. The second application I have in mind, and this is my favorite one to talk about, is environmental remediation. So let me give you one example of this. There are many parts of the world where the groundwater, which is going to become drinking water, is contaminated with arsenic. Sometimes that's because of man-made pollution, that is arsenic from industrial processes gets dumped on the ground and then it leaches down into the groundwater. Other times, arsenic is naturally occurring in the ground and thus in the groundwater. And either way, what this means is that drinking water is contaminated with arsenic, and it's difficult and it is expensive ordinarily to remove arsenic from one's drinking water. But on the other hand, if you don't remove arsenic from the drinking water, then the drinking water itself is poisonous. So that's pretty bad. Well, nanotechnology has a certain principle which has led to the invention of a particular water filter. And this was created at Rice University. Chemists at Rice University have created nanoparticles of Fe3O4. Each particle ideally has 3 iron atoms and 4 oxygen atoms. And we can know this particle by names other than Fe3O4, which is sometimes we call this ferrous oxide because it's iron and oxygen. Sometimes we call it iron oxide. Sometimes we call it magnetite. Sometimes we simply call it rust. And the reason why is because at the nanoscale, arsenic binds to rust, or arsenic binds to Fe3O4 or whatever. Actually, arsenic will bind to a lot of different sizes of rust. Fe3O4 is the ideal size. It's most effective. But any kind of finely milled rust milled down to a very fine powder, can work also in getting arsenic to bind to the rust. So the way this device works is that the ferrous oxide particles, whatever their size, whether it's ideal or larger, are suspended in an oleic acid, for example, olive oil. And then there's a container, a clear plastic container, that has a hole at the top to drip the contaminated water in, and it's got a little spigot at the bottom to get the water out. And then what happens is as the water is dripping onto this layer of oleic acid, guess what? The arsenic binds to the rust. And then the arsenic is removed from the water by passing a magnet over the ferrous oxide, because what happens, a magnet picks up iron, and in picking up the iron, it also picks up the arsenic. And one of the reasons why this works is because of the relationship between water and oil. I want to put it this way. If you've ever made salad dressing in a little bottle, you put in the dressing, the flavor of the dressing, the herbs and the spices and so on and so forth, and then you put in a certain quantity of oil, and then you put in a certain quantity of water, and when you're going to use this on the salad dressing on your salad, what do? You shake it up so that everything will be nicely mixed up. You pour it on your salad and enjoy it that way. But then what happens an hour later? What happens when you put that bottle in the refrigerator overnight? Then, of course, the water and the oil separate so that the oil will sit on the top and the water will be on the bottom. Well, the same thing happens in this water filter for getting arsenic out of the drinking water, namely that what will happen before long is that the oil and the water separate. The oil is on the top, the ferrous oxide is in the oil, and now the arsenic is also in the oil on the top, because that way the arsenic has bonded to the ferrous oxide. And then you remove the iron, and in removing the iron, you're also removing the oxygen. And when this was published by that team at Rice University, they said that their result was that they had levels of arsenic in that drinking water that are safer even than U.S. standards for drinking water. And U.S. standards for drinking water are pretty strict. So A on the left is the drinking water originally contaminated by arsenic. And then B on the right is the drinking water for which the arsenic has been removed. Big difference. And now another important point is these water filters can be constructed easily and inexpensively in almost any third world community. In other words, a village in Bangladesh doesn't have to mail order one of these filters from Rice University. They can build this kind of filter, they can buy this kind of filter. What they really need, the hard thing to find, is rust and oleic acid. And you can find rust anywhere, where there are old automobiles that are rusting, or lampposts that are rusting, or iron fences that are rusting. It's not very difficult to get rust. And then have it milled down to a very fine powder. Even if you don't get it down to Fe3O4, you can still get the ferrous oxide that'll work to remove the rust. And then it's not very difficult to find oleic acid. Maybe it won't be olive oil in one place, maybe it'll be a canola oil or something else, but one of the best things about this particular device, which works on a principle of nanotechnology, is that it's simple to put together and it's simple to operate. The third application I want to talk about is carbon nanotubes. And I keep hearing it said correctly that carbon nanotubes are 6 times lighter than steel and 100 times stronger than steel, which means that they have a potential, which has not yet been realized, but they have a potential to reinforce or even replace everything we have that's made of steel. And you think of everything in our lives that's made out of steel, and imagine in 10 or 20 or 30 years that our steel could be reinforced with carbon nanotubes, maybe even replaced by carbon nanotubes. On Tuesday night, I was having dinner with Ibrahim, and we had a talk about this. And when I think of carbon nanotubes, I'm thinking mostly of reinforcing steel and maybe later replacing steel. And Ibrahim reminded me that there's a whole lot other things that are going on with carbon nanotubes. For example, things in microelectronics, which is a very different application, but still an important one. There's a problem with carbon nanotubes currently, which is that the maximum length of carbon nanotubes right now is only several microns, or micrometers if you like, and it's expensive to produce in large quantities, which means that when you only have something of a length of a couple of microns, then that's really too short to reinforce steel, let alone to replace steel. Now, I began to learn about 14, 15 years ago that there are some things which are said to be better now because of carbon nanotubes. Very expensive golf clubs, very expensive tennis rackets, very expensive baseball bats or softball bats, and so on and so forth. And quite frankly, because the carbon nanotubes are only a couple of microns long, I don't really believe that any of those sporting goods are really improved by throwing in some carbon nanotubes. But this leads us to a question, which is, who will find a way to produce carbon nanotubes with a length of, let us say, several millimeters? You could really do some neat things to reinforce steel with carbon nanotubes of several millimeters. And to do this in, of course, industrial quantities, and to do it with good quality control. And I believe that whoever figures out how to do that is going to very quickly become wealthier than anybody else on the earth. And they're going to change our material culture by reinforcing or maybe even replacing the steel we use. Now, I have an idea I want to share with you. If this is done here at Bilkent University because of Chris Toumey's suggestion, then please include me in the patents and the royalties and the equities and the licenses and so on. And I'd be 100% happy with 1%. You know, that'll be more than enough for me, okay? So, actually, what I'd like you to do is not only remember that, it's probably a good idea for you to write that down also so we don't forget it, okay? And you do that, and I'll visit Bilkent anytime you want me to. That's fair. Okay, and so, if we can get to the next slide. I think, okay, and let's get to the next one. Okay, so we cannot say how nanotechnology will affect humanity, and specifically, I cannot say how nanotech will affect humanity if we don't know these certain conditions and problems which characterize the word nanotech, those four problems that I was sharing with you earlier. But we can learn about those conditions and problems and then craft a four-part definition which takes those problems into account and gives us a better understanding so that finally we can begin to imagine realistically how nanotech will affect us in the future. Thank you. Now, before we do your questions, you have to help me with my question. Before I came here, I learned how to write thank you in the Turkish language. But you know what? I don't know how to pronounce that. Can you help me with that? Say again? Thank you. And since you have helped me with that, I'll help you with the last version of thank you, which is the Elvis version. So, you know, Elvis used to finish his concerts by saying, "Thank you very much." And if you ever need to speak Elvis, that's an expression you can use. Okay.
Thank you, Sean.
Try the Gaelic version.
Oh, you know, and in Irish Gaelic, I used to study Irish Gaelic in graduate school a long time ago, and that's Gora Mahagat, so that if you ever need to know that, I'll help you with that.
That's fine. Well, now we can have some questions for Chris. Yes, please.
Well, thank you.
Thank you.
Well, with all humility, first of all, I think nanotechnology is, first of all, being a transdisciplinary science,
science methodology. It's a transdisciplinary science methodology, science. But I think besides all the facts that you remarkably mentioned concerning the materials, the future, etc., but also it has, I think, a non-negligible. Thank you very much. Thank you. Thank you. I'm sorry. Yes. Thank you for your impressive presentation. Well, it's certainly a transdisciplinary science in terms of science methodology. So it has impact. At the same time, I think, and I would like to have your comments on social sciences, because social sciences at the moment, to my modest interpretation, is really under optimality. Why? Because the material is individual and society, and the error margins and the information error margins and the statistics error margins are quite important compared to physical and natural sciences. So in that sense, I think social sciences will learn a lot from the nanoscience and nanotechnology. Besides that, concerning, I think as you mentioned, nanotechnology impact, I mean, at various levels, materials and so on, I think will change tremendously the future. I mean, just from the construction to anything, I mean, so, because the materials are so different, so powerful, or so small, so I think at the end it will be, in one way or another, very important, and it will be quite likely exponentially increasing. I don't know, I'd like to have your comments. Thank you.
Yeah, that's a good question. It's actually a very big question. So let me tell you a little bit about that. I've noticed in the 16 years that I've been studying nanotechnology is that there's a very large body of literature about ethics in nanotechnology. And what I did a couple of years ago was I collected at least 200 papers on ethics in nanotechnology. And there's probably another 40 or 50 at least on top of the ones that I found. You know, they're from various conferences and various journals and books and so on. And I started a project, which I'm never going to be able to finish, which is I was going to read all 200 very carefully and try to write up a consensus of what's in them. And what I have found is that there really is no consensus on ethics and nanotechnology. And I find this peculiar because the US National Science Foundation and the European Science Foundation and other governments and private entities and so on have been very, very generous in funding research on ethics and nanotechnology and other societal and cultural issues. And I find it really regrettable that there is no such consensus in that. One reason is because there are various venues like conferences and journals that will generously include and accept almost any statement on ethics and nanotechnology. A few of them, a very few, are by professional ethicists, but others are by scientists and engineers and philosophers and others. And they're really all over the place, and I find that very, very regrettable. And I'll tell you this: I wouldn't want to have to go before the U.S. National Science Foundation, let alone a panel of members of Congress, and be asked, "What did you do with all this money we gave you to study ethics and nanotechnology?" Because my answer would be, we've produced an enormous quantity of papers on that, but it's like 150, almost 200 standalone visions of ethics that are really unrelated to each other. You know, they're very personal, they're very idiosyncratic, and so on. So I find that regrettable that there's nothing like a consensus or even a synthesis on ethics and nanotechnology. But there are a lot of issues that come up again and again. The one that I see more often than anything else is people wondering about whether nanotechnology will cause environmental harm. And I can imagine that there's not only a potential for environmental remediation, but also a potential for environmental harm. That's something that's very much on people's minds. A second issue that comes up, and I don't think we have a clear vision yet of an answer to this question, but the question is, will nanotechnology exacerbate socioeconomic inequality? Will nanotechnology have the result of making the rich richer and making the poor poorer? And I think that's a very good question, but I don't think we see an answer yet to that question. And then there's something else I see in, you know, I've done a series of exercises on public engagement with nanotechnology, including the Citizen School that I mentioned earlier. And there is something that I find again and again in the lay public when some people become curious about nanotechnology and begin to read about it, which is the question of who controls nanotechnology. And the honest answer is nobody controls nanotechnology. Research which is funded by our National Science Foundation has to stay within certain parameters. Research which is funded by our Environmental Protection Agency has to stay within certain parameters. Research which is funded by the National Institutes of Health absolutely must have some fairly clear applications for medicine and health and so on. But that's 3 different agencies, and there are many more. And then you add, you know, the various EU agencies and various other national governments and so on. So that that question of who controls nanotechnology, the answer is no one really does. You know, different agencies influence, you know, different aspects. So so your question is a good question, and that's basically how I make a living, is studying societal and cultural issues in nanotechnology. But it's a question which is either, in my opinion, either difficult to answer or impossible to answer. So let me put it this way. I can really best speak about my own research, of course. I think the most important thing I've done, I don't know if anybody on the face of the earth agrees with me on this, but I think the most important thing I've done is some studies on religious reactions to nanotechnology. I've also done some work on public engagement with nanotech, because we live in democracies, and whether the scientists and engineers like it or not, we have democratic processes for electing the people who make science and technology policy. And so I think having a wise body of the lay public when scientific and technical policy questions arise, I think that's a good thing. And then the other thing I've done on a more modest scale than the professional historians is that I've written several things about certain moments in the story of nanotechnology. So, for example, in my commentaries in Nature Nanotechnology, I've written one about the Igor-Schweitzer experiment. I've written one about the invention of the scanning tunneling microscope. I've written one, I don't know if you're familiar with the debate between Eric Drexler and Nobel laureate Richard Smalley, which appeared in Chemical and Engineering News in, I think it was December in 2003. That's a very, very colorful incident. And so I summarized that, that event. So those are the kinds of things that I do. And I wish we had better answers to your question, but we don't.
Well, thank you. Very quick comments, with your permission. First of all, concerning the ethics and nanotechnology, I think in reality it's a subset approach, because in reality the problem of ethics must be looked at the set structure. It covers everything. It covers science, it covers. So when we talk in terms of ethics, with all humility, I have a theorem on ethics, it is at the individual level. If you want to convert to the system optimal at the individual level, at the societal level, at the international sphere level, in any case, ethics is a necessary condition. I'm not saying constant, because mathematically it will be erroneous. So it must be in the system as a necessary condition. Otherwise, we'll be always systematically in under-optimality. So ethics, I think, is a necessary condition, not only in the context of nanotechnology, but of everything, including our individual approach to life and science in general. So besides that, I mean, nanotechnology, I think, as science and all others, achievements of human beings, there are positive impacts and negative impacts, nuclear, etc. There's positive impacts. It's the way how we use them, how we practice them. So in that case, you are right. It's linked to the human beings, to the individual, to the society, to the decision systems, etc. So, but it's true that we don't know very much, but I think in any case, it's a tremendous achievement. It's very important as a science, as a technology, especially. But still, its impact will be. I think, and I will finish here, the issue is to maximize the positive impacts, which will change certainly through the time and space dynamics, and minimize the negative impacts. This can be, I think, the approach.
So let me give you 3 perspectives on ethics and nanotechnology that I've seen in my reading of that literature. Some people say that nanotech is very unique, and so it has its own ethical issues. A lot of people writing about ethics and nanotechnology say that, nanotechnology has the same ethical issues as other forms of science and technology, so that we could look at things like the ethics in genetically modified organisms, or ethics in information technology, or whatever, and can derive a vision of ethics in nanotechnology from those previous events, which means then that a lot of people are wasting their time in writing more than 200 articles on ethics and nanotechnology, if you want to buy that. I don't know. The other thing is, I've got a colleague who many years ago was doing a focus group with the lay public and trying to elicit their views on ethics in nanotechnology. And one person in her focus group said, atoms and molecules have no ethics, so there are no ethical issues in nanotechnology. Monica, thank you.
Oh yes, I was going to say that people in polymers, for example, claim that they are the ones that started nanotechnology because it's the nanoscale, and for example, the patterns that these local polymers do, they go far long before. So, they are used also for photosynthesis. So people don't mention that. There were technologies like reading DNA, where you separate molecules. And that's a technology that.
Sure. Yeah. Well,
so I don't know why it just was all carbon.
Yeah. Well, given that nanotechnology is so many scientific and engineering disciplines and subdisciplines, there's not a unified single origin of nanotechnology. There are stories that come out of history of chemistry, and history of genetics, and history of physics, and history of microelectronics, and so on. And if you would put all of them together to make a history of the origin of nanotechnology, it'd be like a couple of thousand pages long. And I'm not going to do that. Yes?
The last question, I guess. I think I can speak now. So while we were exchanging emails about the topic, you mentioned religion. And I thought about that, and we decided on moving with this topic. But could you please comment on a little bit that? Because if you look at the human history, we started with millions of gods. And then with the technology, knowledge, and science, they decreased to a couple of numbers, a handful of gods, and then now we have one. So what would happen in the future when our knowledge and science advanced? How the religion will be affected by that?
Okay. There were several studies, I think they were about 10 years ago, which indicated that when persons in the lay public took an interest in nanotechnology, that it's not realistic to expect them to really understand nanotechnology well enough to judge it. These indicated that, that the default way of understanding nanotechnology would be for people to revert to their religious beliefs. So for example, if people had religious beliefs about genetically modified organisms, then they would use that as a template to also develop their own opinions about nanotechnology. And then another pair of studies that was done around the same time indicated that the more religious people are, the more likely they'll be very suspicious of nanotechnology. So for example, one of these studies looked at 13 nations, 12 in the EU plus the United States. And there was good survey information about attitudes about nanotechnology. And there was also a kind of a scale or a survey of how religious each of these nations was. And the ones that were considered the most secular, which would be Netherlands, Denmark, Germany, Norway, and Sweden, if they were in that. Those were the ones that were most hospitable to the development of nanotechnology. And the three that were most religious were Austria and Ireland and the United States. And on the graph, they're the ones that are most, I wouldn't say hostile to nanotechnology, but I would say suspicious about nanotechnology. So that's a bad thing, if the more religious some population is, the more they'll be hostile to that. I find that alarming. On the other hand, around the same time, there was a pair of focus groups done on lay public understandings of nanotechnology and discussions that come out of focus groups. And one of them was done at the University of Arizona in Tucson. And it was composed of people, it was composed specifically of people who had religious beliefs and religious affiliations. And it had 3 or 4 different kinds of religious affiliations in there. And then the other one was done at Durham in the UK. And this one was a religious group in which they were all of the same religious affiliation. It's a church, a form of the Church of England. And what both of these focus groups found independently was that the religious people had more or less the same feelings about nanotechnology as non-religious people, but that the religious people were much more articulate, much more informed in discussing things like ethical issues in nanotechnology. So, we might say with genetically modified organisms or synthetic biology or nanotechnology or whatever, that scientists are playing God. You hear that expression from time to time. Well, some people just say that and cannot elaborate on it. But what these 2 focus groups found was that the religious people can really explain and develop and elaborate the idea of scientists playing God for better or for worse. And so what both of these focus groups, when the articles were published, both of them recommended that religious people should have some leadership responsibilities in lay public reactions to nanotechnology, not to the exclusion of non-religious people, but that the religious people had a contribution to make in the way that they were, quite frankly, more thoughtful and more articulate than non-religious people that were also studied in comparable focus groups. Okay, we done?
I guess we can wrap up this session. That was a very good discussion, very deep and intense. So let's thank our speaker one more time. Thank you. We will be proceeding with the flash presentations. So it is the first time that we are handling these presentations, so please be patient with us. So we can put together, yes. So we will be merging all the presentations that you have sent. The ones that are selected will be coming one after another. So what I will do is I will ask the shortlisted presenters to be ready. It is listed, it's ordered by name. And if I'm not mistaken, the first speaker was Azimati. You are here, perfect. Oh, yes, and indeed, that might be better if they do line up. So we will show up the list again. Yes, so if you can just occupy these seats. Tamam, you're here. Okay. Bir oraya verirsek. Evet, buradan çıkıyor. Okay. Perfect. Şuraya verirsek okay. Bir başlayalım. Okay, now we will be showing you the whole list one more time. So I will ask all these people to just occupy these seats. Azimati, Ali, Elif Duman. Is Elif here with us? Eliza, Hamid, İlkay. I can see most of them. All right, so just a brief reminder about the format that we have. This might be new to some of you, but we see this more and more in the conferences, these type of flash presentations. So this time we will be strictly limiting it with 3 minutes. So when it comes to 2.5 minutes, please keep an eye on me. I will be just helping you out for the last minute. And then you will hear my phone ringing at the end of minute 3. So that is indeed a very hard deadline, so you only have a few seconds just to wrap up your sentences. And then that's it, and then we will be moving on. I will need some help at this point, Engin Hocam, maybe just to distribute the grade list for grading of the candidates. Alright, so there will be a lot of referees that will be grading you. Okay, so let's get started with our first speaker, Azimati Ekiber. Come on. Right, so just wait for my signal.
Okay.
What would be my best position? Şöyle otursam sonradan mı iyi? Which one would help? Okay, so I will be just over there. This will be 2.5 minutes, and then when it swings, this is 3.
Ah, okay.
Yes. So all the slides are following this.
Okay. Hello everyone, welcome to NanoDay. This is my very honor to stand this stage and give this sharp presentation. This is from my previous master project actually. The title was the lubricant oil degradation monitoring by using the contact separation electrification. So the contact electrification is a very common phenomenon in our daily life, even in the natural phenomena. So after the first triboelectric nano generator invented by the John Lewis group in 2012, there are a lot of nice work have been done by the scholars, like a mercury ion sensor, phenol sensor, and a volume sensor, even the water ethanol sensor, just by comparing the electrical output by artificially using the contact separation mode, the TENG. TENG means the triboelectric nano generator. So with this inspiration, we were thinking how we can combine this contact electrification, the one branch of tribology, to the oil degradation condition, oil condition monitoring actually. So out of this inspiration, we think about the triboelectric sensor, and we made this tapping device. We call it triboelectric sensor. And initially, we prepare our sample with the simulation of the engine oil combustion system, and we prepare different sample by pick up them with different time intervals and absorbed by the cellulose paper, and by using contact separation mode of the polymer and the cellulose, oil absorbed cellulose, we got the different signal in terms of the different oxidation time. So this is our overall result, and we can see the ATR characterization peak, the ZDDP, zinc dialkyl dithiiophosphate additive, is very important anti-wear function additive in the engine oil industry. So we can easily see that from the untreated to the oxidation time to 80 hours, it's completely depleted, and this output signal also degraded all the way, decreased all the way. So it's worth nothing that this tribal electrification device can be a very direct and simple indicator for the ZDDP depletion level. So which means we can, and this tapping and the triboelectric contact device serves as an indicator of the service life of engine oil, engine lubricating oil. Thank you very much.
Hello everyone, welcome to UNAM. I'm Ali Kalantari Fard, PhD candidate at UNAM. I've been working on droplet-based microfluidic system. At this work, we tried to make ultra-monodispersed droplets. We analyzed theoretically, numerically, and experimentally the system. Normally, people use a pressure pump in order to make droplets. We propose a method in which we can make ultra-monodispersed droplets by using single ports of the pressure pump and supplying identical pressure. We made analogy. We did a simulation based on that analogy between mechanical component and electrical component. And we got this result that shows when we supply identical pressure from a single port, we can have a better CV. CV shows the coefficient of variation of droplet sizes. So when we increase that identical pressure, we can have better monodispersity for droplets. We did the same for experiment. We did that experimentally, and we used this bifurcating tubing in order to have a single port of the pressure pump and supplied identical pressure. And we had these results, which had a good agreement with numerical results. And we could get CV equal to 0.11%, which is the world record to the best of our knowledge. So far, the best CV which has been reported is 0.40%, but ours was CV was 0.11%. Then we tried to make those monodispersed droplets in different sizes. But how? Because we are using one single port and we are supplying identical pressure, so we cannot change the pressure. So we came up with this idea. By changing the hydrodynamic resistance of those channels, we can change the size of the droplet. We used two different techniques. We used a microplug valve. We had a different configuration for on and off those valves. And we used a screw valve in order to change the thickness of the channel. And by changing the thickness of the channel, we can change the hydrodynamic resistance of the channel. So we will have different sizes of the droplets. As an application, we made a silica particle with traditional method and our proposed method. With traditional method, the CV of those particles was equal to 4%. It is obvious different size of the droplet on top. And for monodispersed silica particle, we got CV equal to 2.2%. And as you see, they are very packed and lattice shaped. And there are some applications for that. Thanks for your attention.
Okay, hi everyone. I am Elif Duman Ergül. I am working with Dr. Olvera Şeker, and I am a PhD student in his lab. And today I will talk about my project And in this project, I produced a bone matrix symmetric scaffold, and this scaffold can be used in bone tissue engineering applications. And in bone tissue engineering applications, where is the pointer? Okay, no problem. Okay, nothing to do. Okay. No. Okay. Okay, fine. Okay.
Just try to move with the
Okay, no problem. Okay. In bone tissue, there is a huge extracellular matrix which is composed of hydroxyapatite. Hydroxyapatite, a specific calcium phosphate crystal with specific calcium phosphate ratio, and this hydroxyapatite is important in bone tissue because most of the bone tissue is composed of this mineral, and it gives the bone its specific strength. And in tissue engineering applications, different hydroxyapatite scaffolds are used to differentiate bone cells or to make bone tissue grafts. And in this study, we made these hydroxyapatite scaffolds by using biological molecules. In this project, I used 3 different genes, and which encodes for alkaline phosphatase, osteocalcin, and osteopontin. These are the proteins found in bone tissue. Alkaline phosphatase converts organic phosphate into inorganic phosphate, which is important for calcium phosphate crystal formation. And osteocalcin and osteopontin regulates the formation of crystals by controlling size, shape, and crystallinity of these minerals. And in this study, I cloned these genes in bacterial systems. I expressed them and I profiled them to assess in vitro biomineralization. And by this way, we can generate hydroxyapatite scaffold, which is generated in an environmentally friendly manner. And these results show how osteocalcin affects the structure of the final crystals. As you can see, in the presence of osteocalcin, the size of the calcium phosphate crystals are smaller, which means that osteopontin inhibits crystal growth, and we can control the size of the crystals, and we can prevent ectopic calcification by using osteocalcin, which means that we can produce our minerals as we wanted, and we can stop the mineralization in undesired conditions. And the other protein is osteopontin, and which we observed that. Okay. Okay, just the second one, Hastings mineral formation, and
thanks a lot. All right. That is, I think, quality. Elisa. So try to have an idea.
Hello everyone, welcome to NanoDay. I am Eliza, and I'm working with Dr. Yegan Erdem. So I will present my master project, which is directed assembly of charged nanoparticles by using electrostatic forces. So positioning particles on the surface in a controlled manner, it's important to design electronic and optical devices. And also printing different of particles on the same surface increases functionality and flexibility of the surfaces. In this project, we used electrophoretic deposition method to obtain this nanoparticle pattern. So we have this two electrodes, and working electrode has patterned metallic electrodes. And when potential is applied across this between these electrodes, electric field is generated between them, and charged nanoparticles are attracted towards the opposite potential electrode surface. So that's how particle patterns obtain the geometry of the electrodes. In the first part of this study, we obtained patterns of one type of particles. So in this case, these are fluorescent green latex and fluorescent red silica particles. And adhesive particles are deposited only on the surfaces of the electrodes, and the gaps between them are empty because these are insulating areas. And so second part of the project was obtaining, as I mentioned, multifunctional surface. So here these two images are from the same surface, and particles are located next to each other. And in last step, composite structures were formed by positioning both latex and silica particles on the same areas, which form composite surfaces. So, and as I mentioned, these surfaces are called smart surfaces, and it can be applied to design, for example, a multifunctional sensor device. So, thank you for your attention.
Good afternoon, everyone. This is Hamid, PhD student at UNAM. I'm working with Professor Kasirga, and I believe that vision is the strongest human ability, if you agree. Everything is more discernible once you see it. So with this introduction, since I'm going to show you some real-time optical images of the CVD growth, transition metal dichalcogenides, TMDCs, which is just very recently accepted in Journal of Nanoscale. The vision actually is our main motivation to see what's going on inside in CVD process, let's say. One of the shortcomings of CVD chambers is that you don't have any access to the growth real time, and you have to optimize many recipes. Some of them are not even reproducible, and there are some challenges. So with this motivation, we designed and fabricated custom-made chamber. It's a compact CVD. Briefly, there are some custom-made reactors, aluminum reactors inside that we can ramp up individually each of them. We have the control of individually of each heater. And as an exemplary of TMDC's growth, this is a series of images of real-time images of salt-assisted tungsten diselenide. So we can produce high-quality monolayers WSE2, but this is not just the synthesis story. We have the control. We can investigate the effect of each parameters, and also we can shut down the chamber at any desired time. So once you're satisfied with the growth, you can shut it down. And also this is very favorable to study the mechanisms of salt-assisted CVD growth. So as we studied this growth, we found that there are two distinguished growth modes, VLS, vapor liquid solid, and VSS, vapor solid solid, that they induces growth. Also, with series of control experiments, we found that actually hydrogen diselenide is inducing the growth. We can control by controlling the volatile precursors, intermediate compounds, we can exclusively promote VLS, either VLS or VSS. Also, we investigated the effect of hydrogen here. this is also studied for the first time, as well as the monitoring the real-time growth. So we found that sending hydrogen, this is very critical at some growth states. We found that due to the lack of hydrogen, selenium, or let's say hydrogen selenide, you may end up with sodium tungsten borons. And finally, just to show off that the ability of our channel, we synthesize both vertical and lateral heterostructures. And as a conclusion, besides real-time monitoring, these chambers, we have the ability to integrate a spectroscopic, we can integrate a spectroscopic measurement to get information.
Hello everyone. I'm Ikachi Köksal'da. Sorry about my voice because of the allergies. My voice is a little bit low. And I'm currently working with Professor Taşbuğar Tüşeker, and we are working on synthetic biology. And my project is about the whole cell biosensors for heavy metals detection in biomedical applications. And we are using whole cell biosensors because we can sustain them, and it's very low cost, and they can produce very rapid responses for the presence of the sensing. And you can see that the whole cell biosensors also have the three parts like their normal sensors, sensing, processing, and actuator. This sensing part translates the information to information that can cell process, and then an actuator, in this case we are using SFGPA fluorescence protein, and then we are quantifying the amount of fluorescence protein according to the time, and then the concentration. You can see on the right side that we are producing a copper biosensor, and you can see we are changing the circuit so that it can produce very different responses according to the concentration. And then you can see the time-dependent manner on these other graph bars, and you can see the cadmium biosensor system. And you can see from here that we engineered the lead biosensor system, and you can see from here, this is the arsenic biosensor, but the difference of the lead biosensor is when we engineer the system, you can see it changes from analog to the digital circuit. So now we are already optimized the copper and lead biosensors, and we combine them in an imply gate, but we're working on other logical gates for combining this whole heavy metal biosensors so that we can detect them in a very short time, and we can use them on site instead of taking the sample to the laboratory. So it's my project. Thank you.
Hello everybody, I'm Melis Özkan. I'm a master student in UNAM, and I'm working with Associate Professor Dönüş Tuncer on molecular photosynthesizer. In our project, we designed 5-rotaxane-based photosensitizer for photodynamic therapy. Here, this is our drugs, supramolecular photosensitizer. Here we synthesize it through catalytic self-treating reaction between alkyne functionalized porphyrin and picolit 6-uril, CB6, which serves as microcycle and catalyst for that reaction, forming triazole groups, which results in 5-rotaxane, our supramolecular photosensitizer. It has ability to produce singlet oxygen very efficiently. As you can see here, the first thing, this is the singlet oxygen generation capacity of that molecule. Here, it turns triplet oxygen into singlet oxygen, and we used that ability to in photodynamic therapy, first on E. coli, gram-negative bacteria, Once we shine white light in the presence of light, it will, we will see singlet oxygen generation. Figure C and D, the dark experiment, C is control, D is dark. We don't see any remarkable effect in the dark, just 9% inhibition in the dark, but in the light we see huge amount of inhibition in the white light. And these are our SCM pictures. A and B dark. The left side is control, right side is with sample. As you see, in the presence of light fight, the cells of E. coli are destroyed. And it's good thing for our supramolecular photosynthesis. The effect in the dark cytotoxicity is diminished. And also we did the same experiments using MCF7 breast cancer cell line. It doesn't show any cytotoxicity in the 300 micromolar, but even 2 micromolar is enough to inhibit that cell lines. That was our project. Thank you for
Hi everyone, my name is Muammer Kanlı. I am working with Assistant Professor Engin Durgun. I would like to present my study about ternary gallium aluminum nitride alloys. Gallium nitride and aluminum nitride can be considered as the pristine cases for these ternary alloys. They have been synthesized recently and they have many applications, namely LEDs, detectors or lasers. Gallium nitride and aluminum nitride monolayers have been studied in many respects, but the monolayer of ternary alloy has not been studied yet. So our motivation was to study to see the stability of this ternary alloy and check for the characterization. So as you see, as method, we have used ab initio or first principle methods, namely density functional theory. We used WASP and PhonoPy codes and characterize all the properties. As you see in here, we obtained the crystal structures of these ternary alloys. As you see, the lattice constants give a linear decrease with respect to aluminum content, X. We made phonon distribution and molecular dynamics calculation to check for the stability of these structures. And according to our calculation, we obtained that these ternary alloys are stable at 0 Kelvin and preserve their stability at 300, 600, and 900 Kelvin, according to our phonon distribution and MD calculations. From now on, I will show electronic properties, thermal properties, and optical properties, and conclude. For electronic properties, as you see, I didn't put for crystal structure and electronic properties the gallium nitride and aluminum nitride versions because they have been studied already. For band structure, you see we have actually a very soft shift from gallium nitride bands into aluminum nitride bands as you increase the X value. So X value, namely, starting from 0.25, 0.50, and 0.75. So the indirect band gaps, as you see, gives an increase, but different from the lattice constant, which gives linear decrease. This increase is non-linear and with a negative Bowing parameter. So this increase is not linear, but with negative Bowing parameter. Then for optical parameters, optical properties, the imaginary part of the electric function, I used that part and obtained the optical properties. As you see, the absorption onsets emerges out on a near infrared zone.
Hello everybody. I'm Murat Serhatlıoğlu. I'm a PhD student here under supervision of Dr. Çağlar Elbüken. So we are working on lift force. Lift force is in the nature from microwave to macrowave to microwave, and we are working in this generated particle migration behaviors in microfluidic environment using Newtonian and viscoelastic non-Newtonian fluids under combination of hydrodynamic flow and external electric field. And we are applying in a microfluidic channel both pressure flow and electric field, and we are observing what happens to the particles inside it. And normally in a pulsar flow, we have a curvature in the flow velocity, but when we think relative to particle, the velocities is changing in both sides of the particles, and here, and the particle has a shear gradient lift goes to the wall. When we apply electric field for this Newtonian solution, what happens then we change this lift position because of slip velocity generated thanks to the electrophoretic force of the particle. The particle goes to the center of the channel. And when we change the direction of electric field in this case, now it's vice versa, again going to the wall. So when we, instead of a DI water, when we use PO-based, polyethylene oxide-based viscoelastic solutions, we see a different phenomenon. Now we have polymers here, and the polymers are highly stretched in high shear rate region and lowly stretched in low shear rate regions, and it generates elastic lift toward the center. And when we apply electric field again in the second part, and now we are seeing that this shear gradient is modified around the particle, and now particles move towards the wall. And when we change the direction of electric field, again it's going to the center. And this is totally different from Newtonian dynamics. And then we change this to polyelectrolytes, like hyaluronic acid or lambda DNA type of solutions. And we use hyaluronic acid here, and we observe different case according to PO-based solutions. We observe like it's working like a DI water. Now particles are going to the wall in this electric field direction, and when we change direction, now particles are going to the center like a DI water. And now we are hypothesizing that this polymer here is also changing their position because they are polyelectrolytes. They are affected by the electric field, and they are affected by the electrophoretic force. And now we design another experiment to prove that we apply electric field in a three-arm channel, and we collect the samples from here and from the center and from the wall. And we calculated their concentration with size exclusive chromatography that we observed here that on the center on the wall and on the center and on the wall for two different electric field directions, their concentrations are changing, which proves our hypothesis in this case. So we are concluding that for different polymer solutions, either neutral or polyelectrolytes, the lift direction flips. And for Newtonian solutions, it's different. So we are making a unified model for three of them, and we are concluding that this non-uniform viscoelastic opens a new age for 3D electrophoresis studies. Thank you for listening.
Good afternoon, everyone. I am Nimat Ayrpur, PhD candidate in DEMIR Research Group. It's my pleasure to be here for presenting my poster. Thanks for the selection committee. So, in this study, for the first time, we proposed a structure which combines the colloidal quasi-2D nanocrystals with the 2D semiconductors. And we investigated the energy transfer process in this hybrid. You see here the schematic of the energy transfer process, which the FRET type of the energy transfer is an electromagnetic process where the excitation energy of a molecule like donor transferred to another molecule like acceptor. So the schematic of our proposal and the fabricated devices shows in this schematic where our colloidal nanoplatelets, quasi-2D colloidal nanocrystal, is separated by their electric spacer from a monolayer of the molybdenum disulfide, which acts as a sinking layer of the carriers which generated in our donor. Then the energy transfer process depends on a number of parameters you see here. After fabricating the devices, by using time-resolved fluorescence spectroscopy, we looked at the fluorescence decay curves of our samples. You see by decreasing the dielectric spacer, the fluorescence decay curves is accelerated. It shows up, we have energy transfer from our donor to the acceptor. So by using these data, we calculated the rate of the energy transfer and also efficiency. As you see here, below the 10 nanometer, we achieve ultra-fast energy transfer, which to the best of our knowledge is the fastest one, and it reached up to 268 1-hour nanoseconds of transferring the exciton's or carriers from our donor to the acceptor. Also, below the 8 nanometer, we achieved remarkable near unity of excitonic or carriers transferring from our donor to the acceptor. In addition to these, thanks to the strong localization of the electric field in our donor and in our donor layer and accepted layer, we achieved D2-2 for the first time of energy transfer. It opens new insights about behind the physics of the energy transfer in such a hybrid. And also thanks to the layer-to-layer dipole coupling, which comes from the geometry of our donor acceptor, we achieve extraordinary long force-through radius, which we reported 33 nanometer. Also, for a future and outlook, this combination can be used as a highly efficient for the detectors and the multi-external photovoltaic devices. Finally, this study has been appeared up a couple of months ago in ACS Journal. Thanks for your attention.
Hello, my name is Onur Erdem. I'm a PhD student from the Electrical Engineering Department of Bilkent University, and my presentation is titled Orientation-Controlled Self-Assembly of Colloidal Quantum Wells. These studies mostly revolve around the colloidal quantum wells, or nanoplatelets, as we like to call them. They are quasi-two-dimensional nanocrystals, and they have intrinsic anisotropy, which makes them even more interesting. Basically, what we want to achieve is to control their orientation in solid films. Here we see a mixture of both orientations. They can be either parallel to the surface, or face down, as we call it, or they can be in vertical orientation, or edge up. So usually in an ensemble, there's a mixture of both of these orientations. What we want to achieve is, we want to somehow control their orientation and make them orient in a single orientation for a single ensemble. To achieve this, we use what's called the liquid-air interface self-assembly technique. And thanks to this technique, we are able to control the orientation of these nanoplatelets indeed. So in these SEM images, we see, well, we don't see, but basically in this image on the left, the nanoplatelets are all parallel, whereas the image to the right shows that the nanoplatelets are all in vertical orientation. So by creating these ensembles, we studied the energy transfer from quantum dots to the monolayers of non-stacked or stacked nanoplatelets. And it turns out that the energy transfer is enhanced when the nanoplatelets are in vertical orientation, mainly because there's a larger packing factor of vertical nanoplatelets, and also the dipole-dipole interaction strength is greatly enhanced when the nanoplatelets are vertical. And we also verified this experimentally. So from here, we are able to deposit the nanoplatelets in desired orientation as a single monolayer and over very large areas, as large as, for example, 20 centimeters square. So we thought, why stop here? And we moved on to deposit multiple monolayers of these nanoplatelets by applying the same self-assembly technique sequentially. And we observed, indeed, we are able to deposit up to, let's say, 10 monolayers of these nanoplatelets without losing our excellent uniformity. And also we gain excellent control over sample thickness. Our initial studies show that by using these controlled self-assembly of these nanoplatelets, we can actually create gain media that is ultra thin. And we did observe amplified spontaneous emission, which is sort of a precursor of lasing. And this, in short, this self-assembly technique proves to be a benchmark building block for creation of 2D and 3D superstructures of nanoplatelets. Thank you.
Good afternoon, everyone. My name is Rojin Ghaffari. I'm working under supervision of Professor Salim Eldai, Assistant Professor Salim Eldai. So I'm going to Sorry. I'm going to talk about simple periodic colloidal crystals to complex aperiodic colloidal crystals. So nature demonstrates wide variety of patterns formed in far from equilibrium, but due to the limited experimental setups, the studies, the researchers in these areas has hindered. In 2017, Serimoja's group introduced an experimental dynamic self-assembly setup. Briefly, what we do is that we sandwich a solution between two optically transparent glass slides, and we shine femtosecond laser pulses to them here. And underneath the laser beam, there is a very hot spot, which will create a sharp temperature gradient and create Marangoni flows in the sample. Also, the liquid underneath the laser would boil and create air bubbles, which create boundary conditions. The laser-induced Marangoni flows and Brownian motion of the particles will create a feedback loop. As long as the laser is on and we have the Marangoni flows, we will create aggregates, and as soon as we turn the laser off, the aggregates will dissipate due to the Brownian motion of the particles. We were able to observe all the 2D Bravais lattices and more complex moire and honeycomb structures. These are our experimental results. Here you can see all the 2D Bravais lattices. We use Fourier transform analysis to identify our patterns. And also we observed moire patterns and quasi-crystals which are created from two layers of hexagonal lattices rotated on top of each other, and also honeycomb lattices which are created from two hexagonal layers shifted on top of each other. Our crystals are dynamic and will change due to fluctuations and boundary conditions. And our ultimate goal is to draw a fitness landscape of all these patterns and identify the requirements to get each of these patterns. Thank you.
Hello, everyone. I'm a postdoc researcher in Dr. Serim Ilday's group, and I'm going to talk about the cancer metastasis. We were trying to mimic the blood environment because cancer metastasis is the main cause of death related to cancer, and it is a complex phenomenon with several steps, and the dynamics of cancer cells in primary tumor and also in the endpoint defined very well in the literature, and there are several molecular factors which explains that phenomena. But there are limited studies to show the dynamics of cancer cells in blood environment because the mostly used method is microfluidic, but it has a defined channel, and it can't mimic the actual physical environment of blood. So we introduced one system to study this undulated topology of blood vessels by just using this random obstacles like this air bubble, and also we studied the effect of pressure, and we studied effect of flow, just to mimic this blood environment in metastasis. And as you can see, we studied with 5 different types of cells, ranging from healthy cell, normal-like epithelial cell, to mesenchymal cells. we observed different kind of behavior when they face with random obstacles. The epithelial cells preserve their spherical shapes while this mesenchymal cells increase their contact area. And also we studied effect of pressure, because mechanical pressure is really important. During metastasis, they encounter mechanical pressure all the time. And we observed that the behavior of epithelial cells and mesenchymal cells were different. Okay. And also we studied the effect of flow. We can create different kind of flows just by adjusting the laser power and laser position. We can create laminar flows and vortices. And we also observed that the behavior of mesenchymal cells were different. They were more adaptive to the harsh physical conditions. And as a conclusion, we introduced a dynamic, manipulative, and adaptive system to study the dynamics of cancer cells in circulation. And we observed that mesenchymal cells were more adaptive. Thank you.
Right, so my name is Salha, and let me just jump right inside. What I've been working on is actually CMUS kept their capacitive micromachine ultrasonic transducer, which are essentially speakers and microphones. So normally when you think about them, they are in audible range, but what I've been working on is an ultrasonic range. So CMUS have been around for quite some time, but they are normally for waterborne applications. But what we are trying to do is something different. We try to work on airborne applications, one of which you might have heard of Kinect. Like Kinect is something that uses image processing to read the gestures. Instead of doing that, what we did, we are using acoustics for that specific purpose. Our approach on that thing is we started working with the electrical model. We define an electrical model. Okay, it's working. We try to simulate this thing. We want to know if it's really going to work. We do some FEM analysis to verify these things as well. And once we are done with that, we started with the fabrication. So this is a very customized fabrication process in which we come up with a mass design. We have two wafers. One of them is a Pyrex wafer and an SOI wafer. We go through a very rigorous fabrication process that involves, towards then, we do an anodic wafer bonding as well. Here are some pictures of during the process that was done. Once we are done with this thing, we had to cross-verify these things. Like we started with the characterization process. In the characterization process, we initially start testing it with the microphone. We have a well-calibrated microphone that tests this. We have an impedance analyzer that verifies these things, and we try to match this thing as well. So whatever we did before, like the simulation that we do is obviously idealistic approaches, but we try to match this thing later to verify that this thing, what are the differences that come up. After that, we use a speaker and a microphone. We use CMUS in receiver and transmitter modes, and we send some signals, and we try to interrupt those signals and try to check if the beams are being stirred inside or not. So we were able to achieve this thing, and we have this application. We're going to replace this Kinect technology. This is something that we are looking forward to, and we have some biomedical applications for this purpose. Thank you so much.
Okay, so I guess that wraps up our flash presentation session. Let's give a round of applause to all of our speakers. So. To be honest, what they did was indeed much more difficult than giving a 30-minute presentation, so they all did an excellent job. Now it's the committee's job to handle the evaluations. And then we will be meeting again at 4:30 after the evaluations are done. So now it's coffee break, and then please enjoy the posters in the meantime as well.